Hello everyone, and welcome to my channel where I talk about bioinformatics and computational biology, and show how I do some things. If you like these videos, please consider subscribing. In this video, I will show you how we log on to and use a supercomputer. A high-performance computer or a supercomputer is usually a large collection of computing units, CPUs or GPUs that are connected to each other. Thus, supercomputers are sometimes referred to as clusters. You can actually build your own cluster at home by connecting computers together. I once did it with 3 Raspberry Pis. It's very easy, but of course very limited in power. I mean, in the end, it is a Raspberry Pi. There are of course many different types of supercomputer architectures, but we won't get into that. It's not the purpose of this video. Unlike what sometimes is portrayed in movies, supercomputers do not look like this. They look like this. Yep, a command line interface, which is in my view, the most efficient way to use a computer. There are, however, options to use a GUI, a graphical user interface, on a supercomputer, but I never tried it and not sure what I would do with it. A supercomputer is not designed to look cool. It is designed to be fast and efficient at number crunching. Uber number crunching. Most computations that are run on an HPC, a high-performance computer, can run on a local computer. In fact, it is the preferred way that we first code and test our setup on our local computer, which would be obviously massively scaled down and slow, and once we get a satisfied setup, then we scale it up and run it on an HPC. We do this so we won't waste computer resources, nor have to wait for long queues. You will see what I mean later on. HPCs are shared. You can't hog the entire thing for yourself. You can't use an entire supercomputer just for yourself. It doesn't work this way. And if you try, the HPC managing team will be quite pissed off at you. Which brings me to my disclosure. This video is not meant to teach you everything about using an HPC. HPCs are highly sophisticated equipment that are custom made when they are built. So learning how to use one HPC doesn't mean you can use all HPCs. Each one has a different setup, architecture, environment, and rules and regulations. It is not like learning to use Windows and then you can use all Windows computers. No. Here, each HPC is unique. You need to understand the specific HPC that you are using and its specific architecture. So you have to sit down with the managing team and learn. This video is meant to give you just an introduction on how we use HPCs in general, so when you do sit down with your managing team, you at least understand what they're talking about. What is Slurm, what is PBS, what is a job submission, what is a queue, etc. So let's start. So the first thing you should understand is that we do not connect to supercomputers or HPCs by wire. Not like what you see sometimes in movies. No, we connect through the network. But for security reasons, you usually have to connect through the university network, which means you have to be present, connected to the university network geographically, and then be able to access the supercomputer. Of course, this is a little bit inconvenient because sometimes you want to connect to the supercomputer from home. So the way around this is to go to your university network managers and set up a VPN. So they will give you credentials, username and password, and of course the university IP that will allow you to connect to the university through VPN, and you become as if you are inside the university. Then you will be able to connect to the supercomputer. One method I use, which at least works with me because I'm on a Linux, is OpenConnect. You have to say sudo OpenConnect and then your university IP or web link or whatever. They will give you this information. And obviously, when you execute this command, you will be prompted for a username and password, sometimes two-factor authentication, depends on the setup of your university. Then you will be connected through VPN. Once you connect the VPN, then you can SSH into your supercomputer. And SSH works by typing SSH, your username, at your high-performance computer. When you first log on to the supercomputer, you will land into your home directory. As you can see here, this is my home directory, and it has one script called search.py. You do not perform computation on your home directory. You will be assigned a different directory specifically for computation. For example, here I am changing my directory to ibex, scratch, and my username. And now I am in the computing directory. The difference is that the computing directory is usually a different file system specifically designed for high performance computing. Your home directory isn't designed for that. Your home directory is designed for you to store your scripts, your data, things you want to download, upload, and so on. But your computing directory is where you put all your scripts and your material databases and so on, and then submit them to the supercomputer for it to perform the computation. But before we start, we have to talk about modules. And modules are a way for a supercomputer to give you varieties instead of having to install things. Because remember, you are not the administrator of the supercomputer, so you cannot install things at the supercomputer. So here, for example, you can write module avail to see all the modules that are available. For example, you can see a Python 2.7, a 3.6, 3.7, 3.8. It depends which Python you want, you can load it. So here, I'm showing you that the default Python is 3.6.1. And then when I load, I say module load Python /3.8.1, it will load that Python, and now you can see that the version has changed. So it's very important for us to understand this concept of modules so we understand how and what type of variety of programs that we can use in that supercomputer. Of course, if you want, for example, to use Python, for example, almost all my scripts are Python, you can use Conda. And with Conda, you're developing an environment so you can install anything you want in it. And of course, this is very convenient because if you install things, if different versions are not working together, you can just delete it and start again. So you can see here, I'm saying Conda create new test env. And this is the name of my environment. Now we have to activate that environment in order to install Python libraries. And then we can write conda install. And for this demonstration, I'm just going to install NumPy because I have two scripts to show you, and one of them uses NumPy. So there is no need to install a lot of libraries because, again, it's the same concept. Now, of course, I can continue using the environment, but I prefer to deactivate it. Because remember, we are not going to perform the computation on this terminal. And this is the defining difference between using a local computer and a supercomputer. In a local computer, you would execute your script by saying python test.py, and then your script works. In a supercomputer, you have to submit your script to the supercomputer. You are connected to the supercomputer, but you are not connected to the computing nodes. So if you execute your script right now, it will work most likely exactly the way it works on your local computer. It won't be fast, it won't be efficient. No, it's just going to be normal. That's because you're not using a computing node. For you to perform a computation, you have to submit your script to the supercomputer. And the supercomputer will put you on a queue because remember, the HPC is shared. But the question is, how do you submit a script to the supercomputer? How do you send it to be computed? And here is when we talk about the job scheduler. We have two types of job schedulers, PBS and slurm. So here I'm just opening a tmux session and I'm going to divide the terminal so you can see how the two scripts are related. On the left, I'm going to write a PBS job script, and on the right, I'm going to write a slurm script. The first thing we have to write is a shebang. Now, to be honest, I'm not sure if it's needed or not. I always see it in these scripts, and to be honest, I didn't really have the time to test whether it will work with it or work without it, because I don't want to wait on a queue just to find out if this line works or not. As long as it works when it's there, I keep it. So the first thing you have to write is a shebang, which is hash exclamation mark /bin/bash. The tags or the headings for PBS are comment PBS, and for Slurm it's going to be comment sbatch. So here you can see in PBS we say comment PBS dash capital N and then the name of your job. In this case, our job that we are submitting is called test. And it's very important because when you look at the queue, you want to see which job you have. You can submit several jobs, you want to know which one is which. The equivalent that for Slurm is going to be comment sbatch dash dash job dash name equals test. Then we have to decide which queue to use. In PBS, we say comment PBS dash queue thin. That's because the particular supercomputer that I've registered at, which is Aziz Supercomputer from King Abdulaziz University, uses PBS, and it has several queues. One of them is thin. Remember, for your particular supercomputer, you will have different queues. You have to assign your specific queue. Some queues would be for debugging, some queues are for large computations, some queues are for a large number of CPUs, for example, or large number of memory, but less CPUs. It depends on your supercomputer architecture. So you have to decide which queue your job fits in. The equivalent that for Slurm is going to be comment sbatch dash dash partition equals batch. And as you can see here is a very clear example because the Slurm script works at a different supercomputer than the PBS script. So the Slurm script is actually going to be submitted to the Ibex supercomputer, which uses Slurm, and obviously it has different queues. And here you can see the queue is called batch. Then we want to decide how long is our script going to compute. We can't just send a script to the supercomputer and tell the supercomputer, deal with it. No, we have to assign how long it will be computed for. And this is very important. Again, all of this will be figured out when you are testing your system locally. You understand, for example, if you have a simulation, how long does the simulation take? Maybe the simulation takes 4 hours. So of course, you're not going to give it 4 hours because it might cut just before it ends. You might give it 6 hours, you know. But you're not going to give it 24 hours. The reason for this is that when you assign the correct time, the CPU time for your computation, you will move through the queue faster. For example, if you have a script that takes 3 minutes to run and you send the script to the supercomputer assigning it 24 hours, it will wait until there's a slot for a 24-hour computation to go through. That is inefficient because you're wasting your time. The computer thinks you need 24 hours while in reality it's only going to take 3 minutes. So why wait until there's enough empty nodes for a 24-hour computation? What you would do is write 3 minutes, 4 minutes, or 5 minutes. And when the job scheduler sees that it's only 5 minutes, it's only a quick computation, it will bump you up to the front of the line. The job scheduler is called job scheduler because it's efficient. It tries to take the proper decisions to make the computer run efficiently, which means if there are people that are requesting 24-hour computations, why make them go first, spend 24 hours computing, and then make the others that just want 2 or 3 minute computations to wait for 24 hours until the node is empty? No, bump these people quickly, make them perform their quick computation, send the results, and then run the slow computation. So why I'm telling you this? I'm telling you this to justify and try to explain to you why it is important to assign the correct time for the computation. If you don't assign the correct time for the computation, you will waste your time. So of course in PBS, you would assign the time by writing comment PBS-L wall time equals hours, minutes, seconds. And the equivalent that in Slurm is going to be comment S-batch dash time equals hours, minutes, seconds. Then, of course, you need to assign the amount of CPUs that you want, the amount of nodes and CPUs that you're requesting. Again, this is very much dependent on your particular computation. I can't just give you a number. You have to understand the type of computation you're performing. You cannot just copy and paste. Okay? You have to understand this computation. How many CPUs does it need? How many nodes does it need? And the way supercomputers work is that you usually have a node that is comprised of several CPUs. So for example, you might have one node, and within one node you have 24 CPUs. So if you request one node, you have up to 24 CPUs at your disposal. You might want one node with only 4 CPUs, and maybe segment the others, or you might want one node and all the CPUs. Again, it's very much dependent on your particular computation. In my case, I'm saying I need one node and 4 CPUs. I don't need 4 CPUs for the demonstration. I'm just giving you a number so you can understand what they mean. In PBS, we would say comment PBS-L select equals 1 for node, then colon n CPUs equals 4 for 4 CPUs of one node. Of course, I can request 2 nodes, and each node would have 4 CPUs. The equivalent in Slurm is going to be S-batch --mem equals 0. What does this mean? So in the Slurm script, I am requesting a specific memory as in RAM. Remember, sometimes, and this is going to be in one of the demonstrations I'm going to show you now, sometimes you have such a large dataset, for example, for machine learning, you have a large dataset that you need to load into RAM, and you cannot load it in your local computer because you only have 3 gigabytes. But the supercomputer can give you up to, for example, 500 gigabytes of RAM. So you would request that. You can request 100 megabytes, 100 gigabytes, or write 0 to request all that is available. In my case, I'm going to request all that is available. But then you have to say comment S-batch --nodes equals 1. So I'm requesting one node, and then comment S-batch --n tasks equals 4 for 4 CPUs of a node. So I'm requesting one node with 4 CPUs. Sometimes you might not want CPUs, you might want GPUs. Again, it's very much dependent on the type of computer that you've registered at. If it has GPUs, if it has only CPUs or only GPUs or a mixture, it depends. But one way you can request GPUs is to write comment S-batch --gres equals 4. So I'm requesting 4 GPUs. And then S-batch --constraint equals V100. So what I'm requesting is the type of GPU that is V100, a Tesla. I'm not going to run that because my script demonstration does not require GPUs, but this is just the code to show you that if you want to request GPUs for machine learning, for example, this is how to do it. But remember again, your particular high-performance computer might have slightly different tweaks, because remember, they are custom-made. So what I'm writing for you right now might be different than what you need to write. You have to understand your particular high-performance computer. Then there is something very important, because when you submit your script to a supercomputer, you have to tell it where you are. So you have to tell the supercomputer to change directory back to where your local directory is. So this command cd slurm submit dir tells the supercomputer to perform the computation where you are locally at, where you've submitted the position where you have submitted the job schedule, the job script from. Sometimes you might end up with data in your home directory or on other directories and so on. You don't want that. You want them in one place. So it's just standard that you say, change the directory back to where I am. And of course, the equivalent that in PBS is cd pbs o work dir. In PBS, we said we want the output and the error files to be connected together, to be combined together. When we said comment PBS small j OE, that means combine the output and the error files together, because sometimes you might want to separate the output file from the error file. So you can see what output and what errors you've got. In Slurm, if you do not specify what is your output and what is your error files, by default it combines them. I prefer to work this way. I prefer to see the full terminal output. After that, you write your script. If you want to write a bash script or call a Python script, for example, say Python your script and so on, this is where you would write it. If you want to load a module, you would load a module, then activate an environment, then run your Python script. Whatever you have to do to make the script work, this is where you write it here. So in our example, the first thing we're going to do is we're going to run a Python script, okay? But instead of loading a module and activating the environment and running the script and deactivating the environment and so on, I'm just going to call the Python immediately. So I'm going to say home, my username, conda, env, my env, remember the one that we've installed numpy env, the test env, binary, and the Python. So I want to use that Python that is, that is connected to that environment, and call my my script. So let's look at the first demonstration, the tensor.py script. And the tensor.py script is very simple. It's just building a tensor, a large tensor. And the tensor's constituents is just values between 0 and 1. But this tensor is very large. It's 1000 by 1000 by 1000. Okay, it's extremely large. And the script basically just builds this tensor and prints its shape. This tensor does not run on my local computer. I have a local computer, a MacBook Pro 2011, if I'm not mistaken. I didn't buy it. Someone gave it to me. So it's not really a powerful computer. It only has 3 gigabytes of RAM. But when we run this script, you can see that it cannot run. It gives you a memory error. Okay, so this demonstrates to you that this script does not work on my local computer. Now let's go and submit it to the supercomputer. Before we submit a job, let's look at how do we know that we've submitted the job. And in Slurm, you say SQ, and in PBS, you say QStat. All right. So basically, it's Slurm Q, SQ, to see everyone's queue. If you just say SQ, you see everyone who has jobs that are submitted, the ones that are working, the ones that are hold, the ones that are being queued, and so on. And if you say QStat, it's the same command but for PBS. Okay, so if you say QStat, you see everyone's submitted jobs. Of course, if you don't want to search through everyone's, if you don't want to search for your submission out of all the ones that have been submitted currently, you can just say SQ so for Slurm it's going to be SQ-U for user and then your username. And you can see here that I don't have any jobs submitted, so my queue is empty. Now let us submit the job script to the supercomputer. And to submit in Slurm, you say sbatch and then the script name. And now when we look at the queue, you can see here the job ID is 11573637. The partition or the queue, that specific type of queue that we've submitted to, is called batch. The name of my job, my username, my state, and the time that has elapsed is currently being run, so 5 seconds has elapsed, and the number of nodes that I'm using up, and the name of the node, Of course, if I'm using 2 nodes, there'll be 2 names under the node list. Once you check your queue and you see, and your job disappears, it means it has completed. And when you check your directory, you'll find a slurm dash the job ID. Let's open it, let's see what's inside it, and you can see the script has been executed to completion, which means the script built the tensor successfully without any errors and printed the tensor shape. This shows you that I was able to utilize more than 7 gigabytes of RAM, which I couldn't have utilized in my computer because I don't have this amount of RAM, but the supercomputer does. Now, other commands you might use is qdel for PBS or scancel for slurm and the job ID. So sometimes, for example, you might submit a job by accident. Or for example, you might submit a job and you decide you want to cancel it for whatever. You don't want to wait 24 hours until it goes to completion and returns and you know there's going to be an error. No, you can just cancel it. So you say scancel and the job ID. And the same thing with PBS, you say qdel and the job ID. Now let's talk about something else that we can utilize the supercomputer with. And that is an array. Now I've showed you the first example, which is utilizing a lot of memory. Okay. There are obviously other examples where you can combine CPUs together and for example, like MPI, combine them so you can perform faster computations. And the third way is to repeat your script many times, which we call an array. And you can see here in Slurm, if we want to utilize an array, we say comment sbatch dash dash array equals 1 to 4, 1-4. What this basically means is that I want to repeat the execution of my script 4 times. What will happen is that when I send this job to the supercomputer, it's not going to perform one computation. It's not going to request one node. It's going to request 4 nodes, which means that it will effectively run my script, the same script, at 4 different nodes at the same time. The same thing you can say in PBS. You can write comment pbs.J 1 to 4. Why would we need to repeat our script? Well, sometimes you run Monte Carlo simulations. And Monte Carlo simulations, every time you run them, because they utilize randomness, every time you run them, it gives you a different output. And sometimes you want to collect these outputs in order to make a meaningful result. So now let's look at the coin.py script. The coin.py script, as you can see here, is a very simple script. And the only thing that it does is that it calculates the probability of you getting ahead after you've flipped a coin, virtually flipped a coin for 1,000,000 times. Okay, so you can see here I have 1,000,000 trials. I flipped a coin 1,000,000 times. And what is the probability of getting heads? Obviously, we know the probability is going to be 0.5, but that's not going to be exactly 0.5 because this is probability. Okay? So every time we execute this script, it performs 1,000,000 trials and outputs the probability. So sometimes it's going to be 0.51, 0.49, 0.5001, and so on. Every time it's going to output a different result. Now, when we submit this script to the supercomputer, it will execute the script 4 times because I've requested 4 nodes. So you can see here, my job ID is 115733639_4, which means this job ID is being repeated 4 times. And when it is done, you can see that I have 4 outputs. And if I open each of these files, you can see that the output is different. So in the end, this is a small demo on how we use supercomputers. Anyway, I hope you found this demonstration useful. Thank you for watching.